There is a very interesting method to find the Laplace transform using what they call the convolution method. So let's talk about what is the convolution method. Normally we expect that the Laplace transform of a product equals to the product of Laplace transforms. But actually that doesn't work. Instead, what happens is it's actually coming from the convolution product. So let's try to talk about what the convolution product is. So the convolution product is defined like this. So we use the notation star for that. So it's a star notation. Uh, so how to define it? It's from 0 to t f tau g t minus tau. So what happened? One is a tau, the other one is a t minus tau. And then we can actually prove that it doesn't really matter which one you put the tau and which one you put the t minus tau. So you can show that these two are the same. So here what happen is you switch that. So you put the t minus tau to the first one and tau to the second one. Why we need two? Because you can see that sometimes it's easy to use one over the other. So depending on how complicated it is. So for the complicated one, we normally put the tau. For the easy one, we normally put the t minus tau. And also because of this result, you can see that this product is commutative. In other words, f star g equals g star f. So it's like a nice property to remember. And we can use this in problems. So you can see that how we use this idea. And then we have this most important result. So what is it? It says that the Laplace transform of the convolution product is actually equals to the product of Laplace transforms. So that's the interesting part. It's actually equals to the product of. That's what we expected. But what happened here is product is the convolution actually. So if you take the Laplace transform of the convolution, you get the product of Laplace transforms. In other words, we normally write it like Fs and Gs. So Fs is the Laplace transform of the f function, Gs is the Laplace transform of the second function. So this is a very important result to remember. So this is what we call the convolution property. Okay, you can remember this as CP, the convolution property as abbreviations. So we had FSP, SSP, this is like CP. Okay, so let's look at some examples now. So before we do the actual problems, let's try to evaluate few convolutions. So let's try to look at some of these convolution products. So let's look at the first one. So let's see what's the convolution product between 1 and t. So if you use the definition, you can see that this is, you can write as 0 to t 1 time, that's the first function. For the second function, which is t, I'm going to put t minus tau. That's what the definition says. So the first function is 1, so it doesn't really matter what parameter you put. Second function is t, so you replace t by, so what happened? The first function is 1, so even if you replace by tau, it doesn't change, it's a constant. The t, if you replace by t minus tau, it got t minus tau, so that's what we have here. And then you integrate with respect to the new variable tau. And you can see that, and also, if you switch the other one, if you look at the other version, what happened here? 0 to t. So the first function is 1. For that function, I'm going to put t minus tau. But when you can see that when you put t minus tau, it doesn't change. It just get 1. So it's a 1. I put the t minus tau for that function, and for the other function, I put 2 tau. So you get that. So you can see those are the two different integrals from the two different versions of the definition, and you can clearly see that the second one is easy to integrate. So we can use that one to integrate. Now you can see when you integrate, you're going to get this tau squared over 2 evaluated at t and 0. When you evaluate, you get t squared over 2. So that's the answer you get. And you can see that even if you do the other one, you still get the same answer. Just to see that, let's do the integral. So what happened is 0 to t. And then here, your variable is tau. So let's write it. So what we're trying to do is t minus tau, d tau. And be careful here, your variable is tau. So that means t act like a constant. in this case. So t acts like a constant. So it's a constant, and how to integrate? So you can see that it's going to be t tau minus the second one is tau squared over 2, and then that's integral, and then you can evaluate at t and 0, and you can see when you plug in 0, it is 0. When you plug in t, you get t squared minus t squared over 2, which is t squared over 2. So you can see that it doesn't really matter. So you get the answer in both ways, but one is easy to integrate compared to the other one. So you can see this one is easy to integrate. So that means, so when you get a problem like that, always think about which one is easy and then write that one, and then you can proceed with that. Okay, let's look at the next problem. So as the next one, let's do t convoluted with t. So that means by the definition, it is 0 to t. For the first one, we're going to put t. For the second one, which is t again, we put t minus tau and t minus tau, and then d tau. And then what we're going to do is we need to distribute this. How to integrate this one? You have to distribute that. You can't do term by term. You have to distribute. So let's do that. So 0 to t. When you distribute, you get t tau. We write the t first minus tau squared and d tau. And you can see that this is like you can integrate term by term. So t is a constant. Act like a constant. So you get t squared over 2 from the first one. From the second one, you get t cube over 3. That's what you get. And then you're going to evaluate this at t and 0. So when you plug in t, the first one is going to give you t cube over 2. The second one going to give you t cube over 3. And if you simplify, this is like you're subtracting 1/2 minus 1/3. If you take the common denominator, it is 3 minus 2 over 6, which is 1/6. So that means it is going to give you t cube over 6 as the answer. So let's look at the next one. So as the next one, we have t convolution with e to the t. So if you write the definition, so you get 0 to t. Let's say you put the t minus tau into the first one, because here you can see this one is like e1. So what we can do is we can put the to the other one, because it's a polynomial one, we can put the t minus tau there. So that means it's going to be t minus tau for the first one. From the second one, e to the tau, d tau. So what you get. And then there are multiple ways to do this problem. So one way to do this is you can distribute this first, and you can do term by term. Or you can directly consider the first one as just 1 and the other one with the other one. So just like that. So let's try to do the first method. We just create this like this. And if you do that, so what's going to happen? So you can see, so you can have the di table. So it's a d and the I, the shortcut method for integration by parts. So the first one is going to be, so we go with the d and the I. So it is t minus tau for the first one, and the other one is e to the tau. And here, remember, t acts like a constant. That means when you take the derivative, it's going to give you -1. And if you integrate the other one, you get e to the tau. And you take the derivative again, you get 0, and you get e to the tau. So that's what you need. And then we multiply this one, first one with the plus sign, second one with the minus sign. So if you multiply, now what we do, we can write the product here. So the answer is, first you're going to get t minus tau times e to the tau as the first one, and it's plus, and the next one is minus again plus, so you get e to the tau. You can evaluate these two at t and 0 according to the definition, and then you can see when you plug in, now what happened when you plug in t, this term get cancelled out. So you get e to the t only from the second term. And when you plug in 0, and you can see that tau equals 0, so you get from the first term, you get minus t, because this is the bottom limit, that means there's a negative sign. And then when you, and from the last term, you also get a negative 1. So that's the answer if you do it this way. Now let's say you switch the definition and use the other version. So if you write the other version, so what happening here is again 0 to t. So the first one you put tau, for the second one you put t minus tau, d tau. So now see how we can do this one and see whether you should get the same answer, but see how things gonna work around. So what we do in this case is, so you're gonna write the di table again. So di. So again d here is tau. The I1 is e to the t minus tau. And then as before, take the derivative is 1 and take the integral. But when you take the integral, be careful. Here the variable is tau, that means that's the coefficient, negative 1. So that means you just divide by negative. So what happened here is it just negative e t minus tau when you take the integral. And again when you take the derivative, you get 0. And when you take the integral again, negative, another negative sign comes out, so you get t e to the t minus tau. So try to understand this argument here, because here t is a constant, only the tau is the variable. So that's what happened. And again, now we write the plus and the minus. So we can write the answer now. So that means according to this one, so it's going to be, so the first product is negative tau e to the t minus tau, and then next one is again negative e to the t minus tau. So what we're going to do now is we can evaluate at t equal t and 0, and you can see that when you evaluate at t, so what will happen is these terms, this is 0 and this is 0, so you only get 1 from this one. So that means you're going to get negative t and negative 1. So you get the last two terms first. And then when you plug in 0, so you get it's a negative. And when you plug in 0, you can see first term is 0 because of the tau. So you get a negative e to the t from the next one, because tau equals 0, you plug in tau equals 0. And then you can see this again simplifies to the same thing, et minus t minus 1. And there's another method to do this one. Actually, that's much quicker. So what's going to happen, there's a third method. So let's see. So I'm going to write it like that. So we start with the same integral, 0 to t, and then tau e to the t minus tau d2. Now we do a slightly different step here. So what we're going to do, we can actually pull this term out, because that's a constant. That does not depend on tau. So we can pull, not a constant, but it does not depend on tau. So we can pull it out of the integral. So we can write this one as e to the tau, e to the t, and then write the rest, 0 to t, tau e to the negative tau d2. And then you can do this again as like a table like earlier. So the table will be very similar to this one, except there's no e to the t term. So that means you can write the answer directly looking at the previous table. So it's going to be e to the t, which is a factor, and then the rest is going to be negative tau e to the negative tau. You can just get the answer from the top, because just cut down the e to the t term, and then you get minus e to the minus tau, and again this can evaluate at t equal t and 0. And when you do that as before, so what you get is e to the t. First you get negative t, e to the negative t, negative e to the negative t plus 1. And you can see that once you multiply by e to the t, this is actually going to give you the same answer. So that's the third way to do this. So you can do like in multiple ways the same problem, and you can see some steps are much easier or quicker or easy to understand compared to the other methods. So it will come from the practice because it's really hard to remember all of these stuff. Okay, so let's do look at like another problem. So let's try to find the convolution between et and sin t. These are all common problems, that's why I'm doing these things. You need to know like how to handle these kind of things. So 0 to t, and because of the previous argument, what I'm going to do, we normally put the t term to the exponential one because you can always pull it out. We're going to make it easy. So let's do that. That means we're going to put e to the t minus tau for the exponential one, and then sine, just go with the tau. So that's what we do because that's going to make it easy. So we put the exponential one, we put t minus tau. And then as before, we can pull it out of the integral. So we can pull out e to the t. So you get 0 to t, e to the negative tau, sine tau, d tau. So that's what we get. And then what you need to do is to evaluate this integral. So we can evaluate this integral separately and then plug in here. So let's do that. So to do that, what we can do, we can write the table for those two. So we can start with d and I. So like in this particular integral, it does not really matter which one you're going to pick as d and I. So let's go with e to the negative tau as d and the sine tau as the I. So take the derivative, which is negative e negative tau. Take the integral, this is the sine, so that means a negative cosine. And then take the derivative again, so it's e to the negative tau. And the cosine, so it's a negative sine tau. And we can stop here. The reason is you can see you get a cycle now because you get in the same one again. So that's a cycle. So once you see the cycle, you can stop. That's the idea. So now we can write the answer. So we can write this is plus, this is minus, and the last one is also plus, but there's a sign change. So because of that, we can write the integral here. So what happened? So I'm going to do like a side work here. So that means when you start with e to the negative tau, sine tau, d tau. So what happened? You get the first product, which is negative e to the negative tau cosine tau. That's the first one. Second one also have three negative signs. You can see there are three negative signs because the three negative signs is negative. So again, negative e to the negative tau sine tau, and then the integral. Integral also have only one negative sign, so it is negative. The last one is integral e to the negative tau sine tau d tau. Now what we're going to do, because of this negative sign, you're going to bring it to the other side. So when you bring it to the other side, you get two of them. You get two of the integral sine tau d tau, and on the other side we have this. So you can actually pull the e term out. So if you do that, so you get negative e negative tau out. So you get cosine tau plus sine tau. So that's what you get. Now what we do, we can divide by 2 because we have a 2 in front. So we can divide by 2. So that means that's, you can plug in there. So we're going to go back and plug in here. So it is e to the tau. So we have so half. You can actually write outside if you want. Half. And also there's a negative sign. So you can write all of them outside. So then what happens is, so you get e to the negative tau, and then you get the factor sine cosine tau plus sine tau and evaluate it at t and 0. Now what we do, we're gonna plug in the value. So when you plug in the value t, and then you can see that, so you get this. So you get -1/2 e to the t. So when you plug in t, you get e to the t, negative t. So e to the negative t, and then cosine t plus sine t. And then when you plug in 0, and you can see sine 0 is 0, so this term is gone. Cosine 0 is 1. So you get e to the 0 means which is 1. So you simply get a -1. So there. So that means you can write it inside the bracket. So you can write it like this. So you get -1 like that. And then what you do, we distribute. When you distribute, and you can see e to the t plus e to the t get cancelled out, and that e to the t always goes all the way to the end. That means you finally get the answer like this. So it's going to be 1/2 e to the t minus 1/2 cosine t plus sine t. So that's the convolution that we get as the answer for this one. I mean, there are a little bit of work because this was like long because of that special integration step. Okay, so so let's try one more of exponential type. So let's do the next one. Suppose we have e to the mt convoluted with e to the nt, so m and n numbers. So what happens? So by the definition is 0 to t e to the m tau and then e to the n t minus tau d tau, and as before you can pull out e to the nt term. So when you do that, so you get e to the nt, so you get 0 to t e, and if you combine the reds, you can see it is m minus n tau d tau, and you can see this is just like a regular exponential integral. We know that the integral of e to the kx dx is, so you simply divide by k, so that means it is going to give you 1 over k e to the kx plus c. So because of that, we can write this one as e to the nt. So it is simply e to the m minus n t. What do you want to divide it? Divide by k. K means n minus n in this case. And then evaluate it at t 0. And we assume that m not equal to n. That's like an interesting question. What happens if they are equal? So you can try to do that and see what happens. Because you can see there's a this step is going to simplify when you before you integrate, so you get a slightly different answer. Okay, so I'm going to give you that as a practice problem, so you can try it. And then what you do, you just put the t and c 0 values. So it is e to the nt, e to the nt, and you can also bring m minus n in front just to make the algebra easy. And then you put t first, so it is e to the m minus nt. When you put 0, e to 0 is 1, so you get 1. That's what you get. Now what we do, we distribute. We just multiply through by this, and you can see it simplifies really well, and then you're going to get e mt minus e nt divided by m minus n. Assumption is we assume that m not equal to n. So that's what you get. It's a really nice result. So as an exercise, see what happens if you do emt convoluted with emt, the same one. Try to do this because this algebra would be a little different here. Okay, so let's try to do one more before we actually do the convolutions. So let's do next one. So we have this interesting one which is sine 3t and cosine 2t. So if you look at the integral, this is what happened, which is 0 to t, and let's say you put the convolution t minus tau in the first one, so it doesn't really matter which one, and there's a 3, so don't forget that. So there's a 3, and then you replace tau with t minus tau, the first one, and the second one, which is cosine 2 tau d tau. So that's what happened. But now how to do this integral? So you remember from Calc 2, when you get an integral like that, you had to use trig identities for that. So let's try to do that. So let's recall these three identities. So we have sine A cosine B equal 1/2 sine A plus B plus A minus B. And then let's see what happens if you have sine and sine. So when you have sine and sine, and you can see that it is cosine here. It is cosine here, and also switch the order. You can see A minus comes here first, and then A plus B goes to the second one. And also there's a sign change. It's a negative. So that's the sine A cos sine B. Now let's see what happens if we have cosine cosine. So when you have cosine cosine, and you can see it is again both cosine. So when you have the same type, they are cosines. That's one thing you can remember. And also you can see this is very similar to the first one. They are very similar to the first one. The first one has a sine sine. The second one has a cosine cosine. So the easy way to remember, when you have the same type, they are cosine. When you have different type, they are sine. And in the middle one, when you have sine and sine, and you can see switch the order, and there's a minus sign. So minus sign explain because you have to switch the order. That means one should be minus. If it's plus, you don't have to switch the order. Okay, so these are the identities, and these are very, very useful when you do sine like sine functions. So now let's go back to the problem. So that means your convolution now, what we can do is we can pick A and B properly. So what we're gonna do, we're gonna pick this part as A, this part as A, and we're gonna pick this one as B, and we're gonna plug into the identity. So when you do that, this is what happened. So using the first equation, you can write this one as 1/2 the integral 0 to t, and you can see it is sine. What you do, you add them. So when you add them, when you add A and B, and you can see that you're gonna get 3t minus tau when you add them, plus, and then for the second one you have to subtract them. So when you subtract them, you get sine, you get 3t minus 5 tau, and then you're going to integrate these two. So, and then again, how to integrate this one? You can see t act like a constant, so you only need to divide by the coefficient of tau. So in the first one -1, the second one -5. So when you do that, this is what you get. See whether you get the same answer. So the 1/2 is common, which is outside. So you're going to get sine become cosine. So it's a cosine 3t minus tau plus 1/2, 1/5 cosine 3t minus 5 tau. Why they are positive? Because you can see that integral of sine is negative, and again there's a negative coefficient, so negative get cancelled out. So it's positive. So you're going to get either t equals 0 and t equals t and 0. And when you plug in them, this is what you get. So you get 1/2. The first one is going to give you cosine 2t, and then 1/5 cosine 2t, and then minus cosine 3t when you plug in 0, and also minus 1/5 cosine 3t again, because it's an even function. We use the even property here. Cosine is an even function. So because of that, you get the same term. Now let's simplify. So when you simplify, you get 3/5. The half get cancelled out, so you get cosine 2t minus cosine 3t. So that's what you get as the convolution. So it's a good idea to try different types and see what you get for other ones like sine, cosine, stuff like that. So we just did the sine, cosine one. Okay, so now let's go back to the original problem. So because what we did is we tried to find the convolution. So let's try to do the convolutions now and do the real problems. Okay, so let's do the next question now. So let's do this problem now. Use the convolution product to find the Laplace transform of. So we're going to do the convolution product now. So we know how to find the convolution product now. So let's try to do a problem like this. So let's say find the Laplace transform 0 to t tau e to the t minus tau d tau. And if you look at the definition, and you can clearly see that what you're trying to do here is you're going to find the Laplace transform of. You can see this is a convolution product between t and the e to the tau by the definition. So that means the convolution property says that this is simply equals to the product of Laplace transform. That means this is going to give you the Laplace transform of the first function times the Laplace transform of the second function. So you separately find them and multiply them. And first one we know from the table, Laplace transform of t is 1 over s squared, and then Laplace transform e to the t by the et function. Remember that function? So when we have e to the at, it is simply going to give you s minus a. So because of that, so you can write this one as 1 over s minus 1. So you can leave it like that, or you can just multiply them and write it like this. So you can write it this one as s squared s minus 1. You don't have to distribute, you can just leave it like that. Okay, so that's how we do it using the convolution product. So the most important step is this step. So the convolution becomes the regular product. Okay, so let's look at the next one. So the next one we have 0 to t 2 tau minus 1 times e to the t minus tau. And here clearly see that you put the t minus tau for this one. This is the tau one. So that means this is simply going to give you the convolution. This is the convolution between 2t minus 1 convoluted with e to the t by the definition. So that means what we do by the convolution product, what you need is you need to find the Laplace transform of 2t minus 1 and e to the t. So we're going to find them and plug in them here. You can see 2t minus 1 it's a linear, so you can find them separately. So it is going to give you 2 over s squared and then minus 1. Laplace transform 1 is 1 over s, so you can write it like that. That's the first one. Second one we found earlier, so it is s minus 1. And you can actually simplify if you want. You can simplify the top, first one, taking the common denominator. So finally you can write the answer as 2 minus s divided by s squared s minus 1 as the final answer. So that's how you do something like that. Next we have 0 to t e to the t minus tau d tau. Actually this problem you can do it in 7 different ways. So you can do this in 7 different ways. So let's try to do one of them. What is that? And you can see by the definition, if you look at the definition, there's an interesting thing going on here. So you can see, you can write this one as 0 to t 1 time e to the t minus tau d tau. So that means the other function is 1. So that means this is a convolution between 1 and et. So you can write this one as it is the convolution between 1 and e to the t. So because of that, you can write the answer. So that means 1 means 1 over s and e to the t means s minus 1. So that's the answer for this one. So that get much quicker. And there are 6 other ways to get the answer. Try to see whether you can find the rest of them. So you can even use the first shifting property. and some other nice integral techniques. And also it talk about the commutative property. So if you use the commutative property, your answer get much quicker. You can directly integrate first and then you can evaluate. Okay, so let's look at the next one. Let's look at a slightly different problem. So here there's an issue. You can see that it's not t minus tau, it is 2t minus tau. So what we can do is, because we need to bring it to the right form, so it is not equal to the previous one, it's not like similar to the previous one. So what we do, we can actually pull out one of the et term. So what we do, so we're gonna inside the integral, so we're gonna pull out one of the et term. So when you pull out the one of the integral et terms, you can write it like this. So it is e to the t minus tau d tau. That's what you get. Now you can see, so this is the convolution product as we discussed earlier. And then we have this e to the term. So that means we have to use the first shifting property here. We first try to find the convolution Laplace transform, this one, second one that we already know, and then convolute it with not convolution. When you use the you can shift with the using the first shifting property, because the e to the t term. So the next line you can write this one as Laplace transform of, or you can say e to the t times the convolution, because that's a convolution. So it's a convolution with 1 and et as last time. So that's for the previous problem. So now what we can do, we use the we use the convolution property here. So we can use the convolution property. So if you use the convolution property, you can write this one as find the Laplace transform of this function and then shift it according to this one. So let's do that. So let's find the Laplace transform of the second function. So which is 1 over s times 1 over s minus 1. And then using the first shifting property, you can replace s with s minus 1, because it's we have a 1 in front. Good. So if you do that, then you replace, so you're going to get s become s minus 1, and then s minus 1 become, what happened here? So it is s minus 1 minus 1. So that means finally you get the answer as 1 over s minus 1 and s minus 2. So see whether like there are other techniques to get the answer. So another way, first you integrate this without doing anything. Just integrate first, and then you can think of find the Laplace transform. That's another technique to get the answer. First do the integral. Okay, so there are always like multiple techniques, but this is like much quicker to do this way. Okay, so let's look at next one. So let's look at this very interesting problem. So what we have here is 0 to t tau e to the minus tau d tau. So what you see is, you see that the t term is missing. So how to do, you can do this problem in two different ways. First, one method is just integrate, and then once after you get the answer, you're going to find the transform. The second method is you try to recreate, you try to bring it to the convolution form. So you're going to bring it to the convolution form. That's the second method. So let's try to do that one. So that means what we can do is, we can think about what's the missing term. You see that e to the t is missing. So since e to the t is missing, what you can do is you can write e to the negative to t outside, and then 0 to t, and then tau, and then e to the t inside, along with the negative tau already in there. So you can write it like that. And then now you can see this is very similar to the previous problem, because you can see this is the convolution. So and because of that, so you can write so this part you can write as t convolution of e to the t. So we have that. So that means this is going to be Laplace transform of e to the negative t, and you have here t convolution of et. Now we use the convolution theorem, convolution property. So when you do that, you're gonna get you can write this one as Laplace transform of t, Laplace transform of e to the t, and then shifted by s goes to s plus 1 by the first shifting property because of this e term. Okay, so that means the first one is going to give s squared, second one is going to give you s minus 1, and then we're going to replace s with s plus 1. So if you do that, you get 1 over s plus 1 squared from the first term. From the second term, you can see here we have slightly different simplification here. S become s plus 1. There's a minus 1, so they're going to cancel out. So that means finally you get 1 over s plus 1 squared. So that's what you get as the answer. Very interesting argument here. So we use the convolution, first shifting property, and all of them. But if you just use the integral, you don't have to use any of them because you get an integral and then term by term translation. And see whether if you do that, you get the same answer. You should get. So let's do 2 more problems of different types before we finish this discussion. So as the next one, we have 0 to t e to the negative 2 tau sine 3 times t minus tau. So you can see one is tau, one is t minus tau. That means this is in the right format. So that means it is simply going to give you just the product. So you can write this one as the Laplace transform of the first one is e to the negative 2t. That's the first one. And the second one is sine what? And you can see the actual form is sine 3t. So sine 3t. So now we can directly use the convolution theorem. So if you use the convolution theorem, it's just the product of the convolution. So that means the first one is simply going to give you s plus 2. The second one is a sine. Sine, we know that it is s squared, and then square of the constant term. So that means it's going to give you 9, and the same number goes to the top. So that's the answer for that one. So let's look at the last one. So we have sine tau and sinh t minus tau. So we have a hyperbolic function here. So one has a tau, the other one has a t minus tau. That's in the right format. So that means this directly equal to the Laplace transform of the first function is sine t, the second one is sinh t, and then by the convolution theorem, so you can write this one as first one is s squared plus 1 squared 1. The second one is s squared minus 1 squared 1. And then also you can see that you can simplify this nicely. You can write this one as s to the 4 minus 1 like that. So you can write like that because of the different squares argument. And also I want to tell you this one. So what if you actually see this one 0 to t sine t, not tau, sine t, and then sinh t minus tau. And if you see this problem, and you can see that actually sine t is a constant, so you can pull it out. So you can pull it out. So you can write this one as the Laplace transform of sine t, and then what we have is the convolution between 1 and sinh. So see whether you can do this one. So I'm going to let you try this, and if you know how to do this one, you can put the answer in the comment section. So now you can try these problems as practice problems. And now try these problems as practice problems, and you can leave the answer in the comment section. Thank you for watching.